Lecture 11. Radiometric Image Processing. Remotely Sensed Image Statistics. 1. The representation of data, as it is recorded on digital support, may not be satisfactory for the analyst and the interpreter. Usually, the values actually present in the acquired images are distributed over a much more limited range than the possible gray levels or brightness levels of the display devices. For example, if the radiance values of the scene observed in a certain spectral band are very similar to each other, the image will appear rather uniform and with low contrast. If the radiance values are all quite high, the image will tend to appear very bright and saturate the monitor. To overcome these problems, it is necessary to approach tools of the univariate and multivariate statistical analysis. In fact, the measurements associated with the observations, distributed in the geographical space and therefore linked to the spatial coordinates, whether obtained with active or passive techniques, in most cases constitute a multidimensional set variable according to the number of wavelengths, spectral bands, used in the acquisition phase. This set of measurements resulting in the digital image is generally made up of thousands or millions of cells, so the number of observations is always very large. Remotely Sensed Image Statistics. 2. Here are some basic notions of statistics such as the probability distribution, expected value, normal distribution. A random variable assigns a unique numerical value to each possible observation. The random variable is indicated with x while she indicates the value assumed at the ith observation. The random variable can be of the continuous type, if it can assume infinite values in a certain range, such as the weights obtained from a series of measurements, or of the discrete type, if it can only take a limited number of values in a certain range, such as the head or cross number in the toss of a coin or the dn associated with a cell. The probability distribution p(x) of a random variable x specifies the probability that the random variable x takes the value xi, that is, it is p(x) equals xi. Remotely Sensed Image Statistics. 3. Typical bell shape of the normal or Gaussian distribution function, and underlying areas. Examples of Gaussian distributions: A, with equal mean value and different variance 2, and Gaussian distributions, B, with equal variance sigma 2 and different mean value. Remotely Sensed Image Statistics. 4. A normal distribution is completely defined through the two parameters mean value and variance 2. It also has the following characteristics. It is symmetrical around the mean value. The mean value, the mode, and the median coincide. The area under the curve is unitary. The surface between the two ordinates which are delta, inflection point of the curve, from includes 68% of the total, for 2 sigma from the area is 95% and for 3 sigma it is 99.7%. This is equivalent to saying that 68% of the elements have an x value between plus or minus sigma. Finally, the central limit theorem states that the sum of a large number of identically distributed and independent random variables roughly follows a normal distribution. Image histograms. 1. One of the simplest, but at the same time most useful tools in digital image processing, is the frequency histogram. It is the first step required for image exploration. The histogram is the representation of the statistical distribution function of a dataset. In the graph of the histogram function of a digital image, the index numbers dn appear on the abscissa, normally from 0 to 255, and on the ordinate the frequency f, absolute or relative, i.e. the number of cells of the image matrix that have the same dn value, following figure. If we assume that the measurements associated with the cells, i.e. the DNS, constitute a series of observations of independent random variables, it is possible to interpret each function value as the probability of finding a cell in the image with that gray level x. The histogram therefore represents an approximation of the probability of occurrence of the gray levels, that is, an approximation of the PDF probability density function, PDF, probability density function. The histogram therefore characterizes an image from a statistical point of view, but does not provide any information about the spatial arrangement of the dn values in the image itself. While a single histogram corresponds to an image, a given histogram can correspond to several images completely different from each other. Image histograms. 2. Two satellite images on different areas and related histograms. The image shows the spatial distribution of gray levels, while the histogram shows the frequency distribution of the associated DNS. Image histograms. 3. Each image corresponds to a single histogram, but given a histogram, different images can correspond to it, in which the spatial arrangement of the cells changes with the same DN or gray levels. Scatterplots. 1. In a similar way to the histogram, it is possible to define the scatter plot of a multispectral image as the function that associates the frequencies in the two reference bands with each cell. Scatterplots. 2. Scatter plot can give useful information concerning bands correlation. Point transformation. Point transformations constitute a simple but important class of image processing techniques. They allow the user to modify the radiometry or the gray DN value associated with a cell so that the new gray DN value depends solely on the cell value, unlike the spatial transformations in which, as we will see, the new DN value associated with the cell depends on the values of the neighboring cells. The point transformations cannot modify the spatial relationships inside the image, but they intervene only on the radiometry of the image, and therefore they are also called radiometric transformations. They are available in all image processing systems, and their main characteristics are interactivity, adaptability, user-friendliness, and efficiency. Not being based on a physical model, but being of an empirical type, most of these techniques require a rather good operator experience to provide useful results. Point transformation, contrast enhancing. The human eye is able to distinguish a limited number of gray levels, from 20 to 30, if they are adjacent and well separated. Therefore, the improvement of the contrast makes it easier for the human eye to appreciate the subtle gray variations of an image. It often happens that the digital image has a distribution of DN levels characterized by the fact that the most part of the cells are within a narrow range of values, resulting in a very poor image contrast. This is due to the fact that remote sensing systems, in particular those on board satellites that have global coverage, observe and measure radiance values from surfaces, snow, forests, cities, seas, deserts, during each orbit with responses usually different from each other. The sensors are designed in such a way as to be able, as much as possible, to provide significant measurements on all types of surfaces observed, possibly avoiding saturation effects of the recorded radiance signal. In general, the dynamic range of the radiance signal cannot be changed during the acquisition phase, but in the data representation process is then possible to intervene on the dynamic range of the signal. This type of processing, which tends to change the contrast of the image, is generally called contrast stretching. The algorithm consists of a function that transforms the radiometry of the image, allowing the range of gray levels recorded in the original image to be expanded in order to cover the entire possible dynamic range of the display device. Point transformation, linear contrast stretching. This procedure linearly expands the range of radiometric values X present in the image so as to bring the minimum and maximum values to coincide with the minimum and maximum value of the intensity or gray level scale of the display device. The transformation function g, x, is given by the equation y equals ax plus b, where the angular coefficient of the straight line can also be interpreted as the gain factor between the input signal x and its transforming value y. If the gain factor is a greater than 1, then there is an expansion of the original range. If instead it is a less than 1, then there is a compression, following figure. Point transformation, linear contrast stretching. The most typical formulation of the linear transformation g, x, is given for the DN index numbers of each cell by the following relationship. *sat smiley ____, where DN are the index numbers or gray levels of the transformed image, K0 and K1 and are the minimum, minute, and maximum, max, index numbers of the original image, i.e. the extremes of the histogram, while 255 is the range of gray levels that can be displayed on the screen. The term given by the ratio, 255, K1, K0, being the angular coefficient of the straight line that constitutes the transformation function g, x, represents the gain factor between the input signal and its transformation. A characteristic of this linear improvement of the contrast is that it does not modify the shape of the histogram, following figures, and therefore preserves the relations of radiance. Point transformation, linear contrast stretching. Example of satellite image and its histogram before and after the linear contrast stretching processing. Point transformation, density slicing. 1. With this technique, the continuous scale of gray tones L equals 255 of a monospectral image is divided into a certain number of intervals, and the DN index numbers corresponding to each interval are grouped into a single level of gray which is assigned a new index number DN. The density slicing technique can be considered as a particular contrast modification method. The choice of the extremes of the intervals and the relative new gray value is decided by the user, who determines them according to the objectives to be obtained during the visualization phase and generally on the basis of the information obtained from the statistical analysis of the data. This density slicing technique results in a pseudo-color image. In fact, since the color code is arbitrary and represents a certain range of DNS and therefore a certain range of intensity of radiance, the colors do not have a direct relationship with the original colors of the scene, intended as a RGB system, but they result as a synthetic single-band color image, where the maximum number of colors corresponds to the radiometric resolution. In the following figure, an example of density slicing. Point transformation, lookup table, 1. Each of the contrast modification techniques described above is normally carried out not by means of a direct transformation of the DN associated with the cells of the original image, but through the use of a transformation table, LUT, lookup table. From a logical point of view, a LUT is a vector of n elements, where n corresponds to the radiometric resolution, that convert input data into new outputs values according to a certain transformation function. The DN index number of the input cell defines the position or address of the vector element, and at the output there is the index number DN, contained in that position of the vector. For example, following figure, different DN values are converted into different colors. Point transformation, lookup table, 1. The LUTs are normally inserted as hardware devices between the graphic memories, following figure, where the original image is temporarily stored, and the digital analog converter, whose output signal modulates the intensity of the electronic brush of the monitor. In this way, when performing a certain image transformation, it is not necessary to read all the pixels one by one, transform it and then rewrite it in the new image, but just change the corresponding value in the lookup table. In this way, the use of these transformation tables allows to modify the contrast conditions of digital images practically in real time and without modifying the original data, thus guaranteeing an effective interactivity between man and computer. Point transformation, local transformations, 1. There is another class of image processing techniques that serve to highlight geometric information or details present in the images, i.e. spatial characteristics. These processing techniques can take place either in the frequency domain, and in this case require the use of the Fourier transform, or are applied directly to the image. The latter, in particular, are also indicated by the name of local transformations, since, unlike the point transformation techniques, in which, as previously seen, the value obtained at the output of the transformation is only a function of the value of the single cell, the result of their application depends on the values of the cells belonging to a neighborhood of the considered cell. It is the information of the context in which a certain cell is inserted, the spatial interdependence between the values of the cells, which is responsible for the variations that are perceived as spatial information or geometric details of the image. In analogy with what happens for a signal in one dimension, it is possible to introduce the concept of spatial frequency also for an image, considered as a two-dimensional function. Jensen, 1986, defines as the spatial frequency of an image the number of changes in the numeric value dn of the cells per unit of distance for each part of the image. Point transformation, local transformations, 2. The spatial frequency therefore indicates the rhythm of variation of the gray levels of an image. Slow variations of the numerical values of the pixels of the image correspond to low frequencies, sudden variations of these values correspond to high frequencies, while an image for which the numerical value of the pixels is constant corresponds to zero spatial frequency. Point transformation, local transformations, 3. Even images, like signals, can therefore be considered as formed by a set of many frequency components. Low frequencies LF, low frequency, to which the information relating to mostly homogeneous surfaces or with variations of slow intensity are mainly linked. High frequencies HF, high frequency, to which the information relating to discontinuity between surfaces with different characteristics. The global information contained in an image results from the combination of the two types of information, that of the slow intensity variations from point to point in the image, low frequencies, and that of the rapid variations, high frequencies. LXY equals LF(XY) plus HF(XY). Point transformation, digital filters. 1. The purpose of these techniques is to obtain a noise reduction or a smoothing effect, or to produce an exaltation of details, sharpening, and the highlighting of spatial details, such as linear elements or contours. The filtering in the space domain is achieved through the use of particular mathematical operators called convolution operators. Remember that convolution is the mathematical model that allows a description of the physical process of acquiring measurements by an instrument, such as a sensor. Consider a signal over time represented by xt. If it is input to a system, a modified y(t) signal is found at the output. The system can consist of an electronic device such as an amplifier or a filter, designed to modify the signal in a predetermined intentional way. Or the system could be represented by an unwanted modification of the signal, due for example to a distortion or a noise effect. In general, the properties of the system can be described by a time function h(t), which is called the pulse system function, PSF, or also the system modulation transfer function, MTF. Point transformation, digital filters. 2. Both the original image L and the transformed image R are functions of their spatial coordinates, x, y, in a continuous space, so we have. In order to use the convolution operator in the case of digital images, it is necessary to make explicit the discrete nature of the position variables, so I, j, represent the discrete values of x, y, and the integral is replaced with the appropriate summations to define a discrete convolution. Although the operation is defined for all the values of k and m, it is effective only on a particular neighborhood of the cell of coordinates, I, j, where the g function is different from 0. This corresponds to the convolution core, kernel, or filter core. The convolution core is therefore represented by a numerical matrix, characterized by two elements, its size and values, which determine its effectiveness. Point transformation, digital filters. 3. The convolution operator operates on a digital image through the floating window technique, following figure. The weight matrix, which constitutes the convolution nucleus, is gradually centered on each cell of the image, and each time a new value is produced in correspondence with the coordinates, I, j, as a function of the surrounding cells and the coefficients of the core. Point transformation, digital filters. 4. Considering for simplicity a nucleus of dimensions 3 by 3, the dn value of the cell of coordinates, I, j, which is obtained at the output of the convolution operation is given by the weighted sum of the cells belonging to the neighborhood according to the following algorithm. Where dnij are the intensity values of the pixel at the coordinates, I, j, of the image before and after the transformation. Hkm are the coefficients of the convolution nucleus. H is the sum of the core coefficients, or is set equal to 1 when the sum of the coefficients is 0. The term H is used to keep the new calculated values in approximately the same range as the cell values of the original image. The final result is a new image having the same dimensions as the original image, excluding the edges. As it is not possible to superimpose a core completely on the cells located on the edges of the image, they are not defined. To remedy this situation, sometimes an artifice is used which consists in replicating, mirror, their values along an external frame to the image in order to allow the overlapping of the convolution nucleus also for these border pixels. Point transformation, low and high pass filters. 1. The most used filters in image processing are mainly of two basic types, high pass filters and low pass filters. The following figure shows the differentiated effect of the two types of filter on an image and its histogram. The action produced by a low-pass filter, LPF, is to decrease the spatial frequency of the image, while the effect produced by a high-pass filter, HPF, is to increase the frequency space. Point transformation, low and high-pass filters. 2. The simplest method of implementing a low-pass filter is to apply one of the following convolution cores, respectively of size 3 by 3 and 5 by 5, to the image. This corresponds to calculating the arithmetic mean of the values of the cells around 3 by 3 and 5 by 5 of the cell to be transformed and to replacing the central cell of coordinates, I, j, with the value of the mean previously calculated. Intuitively, this is equivalent to when using a floating mean to smooth the information of a time series data. In the digital image, the convolution operation is repeated by sliding the core of the convolution so that it is centered gradually on all the cells of the image. For this reason, the low-pass filter is also called the floating mean. Point transformation, low and high-pass filters. 3. The HPF, high-pass filter, has the purpose of highlighting the edges or contours between groups of homogeneous cells, and to enhance the areas of transition between different values in the image. The high-pass filter can be operated by applying a convolution core characterized by a positive coefficient for the central element and negative coefficients for the other elements, such as the following examples of dimensions 3 by 3 and 5 by 5. The image resulting from the application of a high-pass filter appears as more sharp and the local detail information appears more evident. Furthermore, the histograms of the images present the typical form of normal or Gaussian distribution curve. Point transformation, low and high-pass filters. 4. Consider the following two examples. In case A, the central cell is surrounded by relatively higher values, while in case B, the central cell is surrounded by relatively lower values. It is evident that the effect produced by the application of the particular high-pass filter, with an amplified central coefficient, is that the lower values with respect to the context, for example 100 in case A, become even lower, while the higher values, 125 in case B, become even higher, with a clear increase in the spatial frequency. Point transformation, low and high-pass filters. 5. Another easy way to make a high-pass filter is based on the following relationship and can be obtained by subtracting the result of applying a LPF low-pass filter from the original image L, X, Y. HPF, X, Y, equals L, X, Y, LPF, X, Y. This effect is illustrated, in the case of a single image line, in the following figure. Point transformation, median pass filter. The difficulty of setting the right threshold value 8 suggests to take into consideration an alternative way, the median filter. In this type of filter, the coordinate cell, I, j, is replaced with the median of the values of the surrounding cells defined by the floating window. Point transformation, directional filters. 1. While a high-pass filter is isotropic in different directions, in some applications it may be useful to highlight transitions along certain privileged directions, directional enhancement. The application of a directional filter to an image produces zero values in homogeneous, constant value zones, low values on low-frequency zones and extremes in high-frequency zones. They are characterized by zero-sum nucleus. For example, the following convolution cores highlight linear structures respectively horizontal, vertical or diagonal. These operations, which are not symmetrical with respect to the cell to which they are applied, are also called derivatives by analogy with the operation of differentiation of a continuous function.